ever on infinite dimensions, dimensional models for the yield curve. And so he owes a big tribute to Marek. It was refused initially, then there have been some works. The second one who did a lot of beautiful work on the topic and who actually referred to this one was Damir Filipovic, who did all his PhD thesis on this topic. Well, then afterwards there have been several things. There is a book by René Carmona. There is an article with Nicole El-Karoui, Ramaconte, and other people, which I'm not very glad about because I have the feeling that they took a bit of my ideas without tribute. So this conference was given in '95. So I just took the slides, but oops. The main idea, and that was also things that Yuri was working a lot at that time, about what I call here quasi-arbitrage. What Yuri, you had another name, it's not almost arbitrage, it's, how do you call it? Yeah, asymptotic arbitrage. And the idea, actually, the reason why I went to infinite dimensions, so I don't know how many of you are familiar with the Hitcher-Morton or the BGM, Brace-Gatterack-Musiela framework for interest rate models. But basically, so the market is made on the one hand, sorry, okay, the market is made on the one hand, you know what, yeah, it's visible, it's too small. What? The thing is,
just sit here. And
yeah, okay. So the market basically is the usual framework of arbitrage theory. So arbitrage theory, what you have is that yeah. So arbitrage theory has it's a dual theory. So on the one hand, you have the instruments who have prices. And you have the dual space where you have portfolios and positions. So the valuation of the portfolio is the product of a configuration, which is a set of prices, and a portfolio, which is a set of positions. Now, in interest rates markets, the base of the prices is the yield curve. Therefore, in fact, there are different ways of representing it. Yeah, that's something strange here. Okay. There are different ways of representing it, but the base is the value of the zero coupon bonds. So you have the Z is the value, and then you can represent it by the forward rate. So the forward spot rate, in which case you see that the value of z is e to the minus interval of f at a given time tt is evolution, and u is a maturity. And you can represent it by the usual yield, which is such that this is in fact the average of the f function over the period of time. It starts with the spot rate, which is the same thing as the yield at 0, and the value of the forward rate, of course, at 0. And so this is what describes the state of the market. And in order to know the price of this market, you have financial instruments. So this is not given directly. It could be almost given directly because, in fact, we have this one. So you have different instruments that are priced in the market. You have bonds, you have swaps, you have strips, which are in fact stripping the bond means cutting the bonds by its coupons, the principal, and making different papers for every single payment, and that gives you information on the price of the zero coupon. And it has also interest rate futures. I'm not talking of options here, I'm just talking of straight instruments. So this gives you information on the state of the yield curve at given points, interpolation points. Now, you have a price of those that evolve through time, and then so you can retrieve partial information on the whole yield curve, but the yield curve is continuous, but you don't have it completely. There is a static version of no arbitrage that says that, I would say it in different manner. If you have no arbitrage between all the existing financial instruments, another way is to say that there is a function f which is positive, so you have no point an anticipated negative interest rate so that you can reprice every instrument correctly, each instrument being itself a combination of their coupons. So you have a version with the bid offer of that, so that you have the existence of a curve that goes between the bid and the offer for every existing instrument. Now, I want to look at it as a function with two entries, the current time and the maturity. And what you can first observe in practice in the market, although this is not something that you can observe in a hard manner because you don't have continuous information, you only have partial information. So when I say it is a random process with respect to time and a regular function with respect to maturity, it's a numerical information. It's not a hard mathematical fact, because you don't have any means to prove that. Just observe that in practice the evolution through time looks like more Brownian motion or something like this, that you have the standard deviation after some time is more or less proportional to the square root of time. And on the maturity side, I can even measure the regularity. I will tell you how you measure the regularity of this function through time. So basically, we get a process in a functional space. We'll have to define which functional space, or another word, you can also call it a random field. So you have in fact a function two variables, but on the it's a random field with asymmetric differentiability. Okay, so now what is the traditional, okay, let me skip the one-factor models. Well, it's important because the one-factor models show that you can have a process only for the short rate, and simply by the fact that the zero coupon is defined as the expectation, what is it? Yeah. Expectation of the forward value of the forward discounting. This tells you that if I know the process for R, then I know automatically the shape of the yield curve at any point in time. Question, how come then with this formula we get multi-factor models and very complex shape of the yield curve? Well, the thing is that in general, on multi-factor models, here I highlight something that R is a Markov process. But in general, in multi-factor models, R is not a Markov process. It has, it uses some extra information, so you have different factors, and R, the short rate itself, is not Markovian. And for that reason, that creates a yield curve that evolves through different factors. So we get a yield curve so the usual way is to write the evolution of either the yields, or I rather write them as the evolution of the forward spot rate. And so you have so df is some UDT plus a combination of some volatility factor here, where the functions are defined on, you see, the function defined on the space, where depends on t, but depends on the whole curve. So a priori, you could have a diffusion equation where the drift and the volatility have a shape that depends on the whole curve. So even the drift and the volatility of a given rate with a certain maturity may depend on the level of the rates at other maturities, or on things like the slope of the curve, or any other feature of the whole yield curve. So, to visualize it, I don't know whether it's visible here. So I get this, I get an evolution of the yield curve in the space H. H is the space of all yield curves, and you get the diffusion process in this space. So to show you what it may look like, and so we have the yield curve like this, that evolves through time. Usually this yield curve is much more rigid in this space here, much more flexible in the front part. So in order to, it's okay? Much more flexible in the front part, and so in order to write the evolution one way, and I wanted also to tell you how to grasp the differentiability of the yield curve, even though you have partial information. So there is a way to do it. So this is, let's say, f of x, and depends on at a given time t. This is the forward rate, so typically you have to think that the yield curve, the yield itself, what I call capital Y, is in fact an average. So it starts from the same point, but then it averages out. So the value of the yield here will be the average of the forward curve on the whole space here. So it goes, it's milder as a growth. But one way to look at it is to decompose f in lambda kt and some phi k of x, where this is some kind of orthonormal basis. So this is oscillatory. It's like a kind of Fourier decomposition, so that you can look at what is the decay speed of the coefficients here. So they depend on t, and the dependence on x is here. So these are typically, this is a technique which actually I did myself, but then I saw that Rosanov did a very good book on random fields, and he describes it very well. If basically the volatility and the flexibility of the curve in the front end is regular across the whole maturity range, then this could be, for instance, simply a Fourier transform, so cos kx, sin kx. But what happens is that we have more flexibility here. Typically, if you do this and you look at the correlation matrix, so you look at the range is from 0 to t, and you look at the correlation, so this is rho of xy is the correlation between the process. So this is let me write it this way: ft of x, ft of y, and so you can do that product divided by square root of ft of x, ft of y. So the quadratic variations. So you find something that is worth 1 on the diagonal, and it decays like this. Now, if you do it with Fourier transforms like this, you'll find typically correlation shape, which is regular. Now, if you use this, what you find is a correlation surface, which is not so regular because it's very narrow at the beginning, so the correlation between those 2 points here drops very fast, whereas in here, you get the same correlation by points which are very further apart. So typically between 1 and 2 months, you get the same correlation as you get between 15 and 30 years. So the correlation matrix is here very wide. It stays close to 1 for a long time. And that means that instead of having a Fourier decomposition like this, you can keep the idea of Fourier, but you have to make cosine k u of x, where u is a function that makes a correlation being equal across maturities. So typically, this is typically the log of maturity. Now, when you look at shapes of this kind, and you can actually, by measuring correlations, you can find the exact function which is very close to the log. You can find out, you can compute those processes. You can fit the value of lambda k every day. You can compute the processes, and by looking at the decay of the volatility of the lambda k, then you find out what is the typical decay of the Fourier transform, what is the typical decay of f hat, or f hat, but I would say, you know, not in u, but of u of x. And you can retrieve the regularity of the function f. So you do that completely empirically. And you find out that in practice, so what did I find? That the forward spot rate was in Hilbert space, in a Sobolev space, sorry, H1.5. And that's so yield is, so f is in H1.5, and the yield is therefore in H2.5. This is purely empirical. You just measure, and okay. So this gives you, you know, where you have a chance to find those curves and how you can drive. So we get those factors. And we know that those factors should keep the curve in this type of space. Now, in practice, if you look at the history of markets, then the yield curve tends to explore a whole range of curves within this space. There is no real restriction of shapes. It tends to be more increasing, it tends to plenty of things like this, but we have seen decreasing curves, we have seen spikes, we have seen all types of deformations, as long as you remain here. And let me put, I should say, a little u here to talk about this change of variable. So that means that it's, which means that f u minus 1 belongs in fact to H1.5. Okay, so okay, so therefore we have we can see the evolution as a semi-group on the space of on this Sobolev space that contains all the yield curves. Now there is a theory. Okay, let me okay, let me thank you. In order to look at the evolution of the yield curve, I made some simple assumptions that in practice you can get close to any linear form any continuous linear form on that space can be represented as a portfolio or close to. So you can, everything that is continuous, you can make it close to, and you have no free lunch assumption, which can be materialized by this arbitrage theory, this arbitrage condition, saying that the evolution the forward curve should lie in the space of in the you see, I mean, the evolution of the curve is made of a volatility of an uncertainty due to volatility and a drift. So somehow it is an ellipsoid. This we have a few modes, and so this ellipsoid is a range of possible plus the drift, and the forward curve should lie in the range of possibles, so that we can apply Gersanov, and Gersanov will tell us that where is it? I didn't put it here. Yeah, Gersanov says that basically the difference between the actual drift and the residual drift, that the difference is in the range of the volatility operator. So now the volatility operator is a quadratic form on H. So this is exactly all the asymptotic arbitrage theory of Fury, where we have infinite dimensions. We have an evolution in H, and so we have this volatility operator, which is a quadratic form, and the fact that we can work out distributions and evolution of the yield curve in infinite dimensions means that through Gersanov theorem, we can pull back the actual drift towards the residual drift, and the difference of the two has to be multiplied by the inverse of the volatility operator. So basically, the change, you see, you have the actual, where did I put it? Anyway, mu is the actual drift, and the change of the actual drift versus the residual drift is such that the difference should be in the range of the volatility operator. In practice, this is where you have a problem, because either you make the assumption that the volatility operator is finite dimensional, which is most of the models that were like AGM, EGM, they just have a finite number of factors. So you have to force, in order to say this is an arbitrage-free model, you have to force the actual drift to be residual drift plus a combination of the factors. Or you say, I have no a priori condition on the drift, it's just the fact that I can pull back the volatility to the residual drift. In this case, you have a little problem, and the little problem is due to the fact that the volatility operator, by definition, has finite trace, because this is the global volatility, so it's a Hilbert-Schmidt operator, and so sigma square has a finite trace, so it has eigenvalues tending to 0, so it cannot be on 2. Therefore, what does that mean in practice? That means that you have possibility of evolution of the yield curve for which you cannot apply Gersanov theorem, and therefore you cannot bring back the actual drift towards the residual drift by applying the inverse of the volatility, which is an infinite dimensional covariance matrix like this one. In practice, it means that you have some options for which, in order to hedge the options with respect to all the possible factors, the hedge portfolio can be not measurable. So here is the thing. So you are in this space H1.5. The hedge portfolio will typically be in the dual of that space. The dual of that space is made of distributions. Those distributions can be approximated by portfolios that are long and short. But in fact, this is where you have a problem. That those distributions can be already, I mean, they can be very awkward because 1.5 is negative 1.5, so that it can represent distributions that are worse than simple Dirac measures. So you need to make some combination of butterfly of maturities in order to hedge a possible portfolio, to hedge again possible changes in the slope of the yield curve. But on top of that, the second problem comes from the following. There is a theory of cylindrical Brownian motion which precisely makes the theory of what is a random process in a Hilbert space. So you have a given Hilbert space, typically a Sobolev space, and you have a process in the Hilbert space with a given differentiability, let's say 1.5. Now, a cylindrical Brownian motion is defined as you don't know what is the process in the Hilbert space. What you know is what is a process every time you apply linear forms. So the way you do it, I have 5 minutes to explain that. Oops. So that's how you describe and this has been very well described by Markior, maybe some other articles. There is also a book by Dabrot and Zapchik who speak a lot of these. The way that you have a Sobolev space, I mean you have a random Sobolev space HS, and you want to describe what is xt, that we call capital XT in HS as a Brownian motion in this space. But this is difficult to define because this is infinite dimensional, therefore this is not locally compact, and it's difficult to define the process. So one way of doing it is to say, given u in H minus S, I can define ux, so x that we call ut is uxt. Now, instead of giving the process itself in excess, suppose that I get this and I have a little x ut. So this is how I'm given the data. So for every portfolio, I have the price of the evolution price of that portfolio. And that is defined for any u in H minus S. Question, does there exist a process in HS so that this is defined? And the theorem is not exactly this, because precisely we have this problem that any volatility operator has to be Hilbert-Schmidt, and therefore it is cannot be onto. The theorem says, so given u dot n, which is linear in u, so we get that x u plus v ft minus ft. Well, there exists for any epsilon, there exists xt epsilon in hs minus epsilon. So you can basically describe, it's the same process because in fact it doesn't really depend on epsilon, but it does not belong to hs. It belongs to hs minus epsilon for any epsilon. So, in other words, in order to get the forward curve here, you have to get the value for portfolios which are less regular. You see, I have to get the value for portfolios which are h minus 1.5 minus epsilon. So this is what we get. So basically, the yield curve can be realized, but you can only hedge the portfolio. Therefore, show that, for instance, swaptions have the Black-Scholes price that they are supposed to have, provided you can hedge with very awkward portfolios that are even more irregular than the observed regularity of the yield curve. Now, the consequence are that you have discrepancies in swaption prices between caps and floors and swaption prices that are really observed in the market, that are not hedgeable, because precisely in order to hedge them, you should have portfolios that are, very unstable across maturities. So this starts, with a geometric theory of cylindrical Brownian motions, and it ends in real distortions in the interest rate market that are observed, and which are specifically due to the fact that it looks like, the theory tells you here is what is the arbitrage theory, but in fact arbitrage theory does not apply as is. Well, I could give you another theorem that I have in this paper, which state that if you take such a Brownian motion and you take the volatility operator and you diagonalize it, and if you take the first n eigenvectors, you basically get the finite dimensional model that leaves away the smallest volatility, and that is very interesting, both in terms of volatility of the remainder, which is by definition because it's the eigenvalues, but also as a max of the volatility of those operators which has volatility of portfolios for, if I look at the norm as a max over a given unit ball of possible portfolios. So we get a double optimization for that volatility which is in this paper. Well, I don't want to take too much time. We're starting late, and I would like to thank you.
So, I am sorry that we are